directing me to this book. It's Robert Fulcum's What in the World? What on earth have I done? There was a little blurb in last month's newsletter, and it just intrigued me, so I checked the book out from the library. Secret Agent X and Mother's Day. My host for a speaking engagement had lodged me in a high-end hotel, the Ritz. The concierge desk was attended by two alert young men in frock coats with the crossed keys of their profession pinned to their lapels. Sleek as seals, handsome Italian faces right out of an Armani advertisement, earnestly eager to assist in any way I might require. But my need was mundane. A new leather band for my reliable old wristwatch, and a new shoestring for my shoe. If I had wanted to buy a new Ferrari, they could have helped me right away. If I had wanted a private jet to take me to Dubai, no problem. If I had needed a table for 10 to honor a Grand Duke, done. Have my mink coat cleaned in an hour? Of course. And tickets for any opera in the world? Piece of cake. But a watch band for an old watch and a shoelace? One moment, please. Consultations in English, French, Italian, and in search of a computer, Rolodex, and telephone books. Nothing. A third character entered the quest. The classy young blonde female front desk manager who had been monitoring the situation. Marcel, she calls, raising her eyebrows. Marcel looks up. X, she asks. Marcel nods. Ah, but of course, X. He writes a few words on a piece of paper and passes it to her. He turns to me. Please wait a moment, sir. Have a seat. Meanwhile, the young woman smiles at me, makes a phone call, writes a note, and passes it to Marcel, who glides over to my chair. There are 2 addresses and a small map on the piece of paper. What you wish is nearby. Shall we send someone for you, or shall we make an appointment? Would you like us to arrange a car and driver? If I had replied that I wished him to carry me on piggyback, he might have. But it was a nice day, so I walked. When I returned with my new watch band and shoelace, I felt I wanted to ask the young woman at the front desk. I don't need to pry into professional secrets, but I'm curious. Who did you call for consultation? What do you mean when you said X to Marcel? Promise not to tell, she said. I will be discreet. Well, when all other information resources of the concierge desk of the Ritz Hotel fail, we call my mom. Your mother? Yes, my mother, Agent X. She's a retired school teacher, lives nearby, knows everybody, and is out and about in the world. We have not stumped her yet. I never realized how much my mother knew until I got this job. She's better than Google, or Yahoo, or Craigslist. Occasionally, the hotel thanks her by inviting her to spend the night as a guest. I think of her as job security. We all refer to her as Secret Agent X. My mom never lets me down. So, happy Mother's Day to Agent X and all her sister agents.
That was perfect, wasn't it? Let's give her another hand. Dr. Joyce Lackey from our program committee will introduce our program. Joyce?
If you needed a physicist fast, whom would you call? Those of us who have heard Duane Ray speak at HGP on topics from quantum mechanics and relativity to DNA and evolution would have no trouble deciding on the answer to that question. With a wealth of knowledge at his fingertips and the skill to explain it clearly, Dr. Ray brings his background in research and development and in teaching to the podium. Dr. Ray's topic today is dark matter, the matter from which the stars, planets, and we are made. The Wikipedia entry for dark matter states, it has been noted that the names dark matter and dark energy serve mainly as expressions of human ignorance. much like the marking of early maps with terra incognita. If this is a subject about which we know so little, what can we learn about it? Even though Duane says he will try to make light of a very dark matter, my bet is that he will give us some solid understanding of just what is and what is not known about this mystery of physics. Join me in welcoming Dr. Duane Ray.
Thanks very much for the opportunity to talk about science again. I really think science is an important part of our society that's really underplayed by a long shot. And every opportunity I have a chance to pound on that drum, I do. Whether we're talking about global warming, genetic engineering, nuclear power, or sending people to Mars, all those things are political issues, and they're also very strongly dependent upon science. I got into a rather interesting discussion already this morning about nuclear power. I'm going to start giving some talks about that. And just as a quickie, I thought I'd ask, how many are in favor of nuclear power? And how many are not in favor of nuclear power? Oh, well, that's an interesting issue. That's a good hot topic to discuss. So we'll be working on that. Okay, well, this morning, we're really going to be talking, however, about the search for dark matter, because dark matter, we really don't know what it is. But before I go into that, let me give you a little bit of background, because some of you might not be too much aware of what dark matter is. First of all, I want to bring you up to date. It's not supposed to do that. Excuse me, I think I have to readjust my thing because it's automatically going through like the previous one was. Set up the show. Do it manually. Okay, there we go. Now we'll go here and start the show, view the show from the beginning, dark matter. That's dark matter as we first found out about it. They didn't call it dark matter then, but in 1933, that's what it looked like. And this is a recent picture. It's dark matter already. Okay, so that's what we're going to talk about. Looks like nothing, almost, but not really. But as I was saying, let me give you some background before we get into that. Just about everything we get from the universe, information about it, comes to us on chunks of energy we call photons. These chunks of energy travel at the speed of light. They have different energies, different wavelengths. And except for a few things like meteors that fall in on us, or we go out to the moon and we bring back a couple 100 pounds of rocks, everything we find out about the universe out there is from these photons, these chunks of energy. Now, some of the photons are red, and they have a fair amount of energy and fairly long wavelength. And as we go to longer wavelengths, we get into infrared, and then into microwaves, and then into standard radio waves. And all of those have very distinct characteristics, definite energy, definite wavelength, and they give us information about that particular region of the wavelength spectrum. If we go to blue and then we go to shorter wavelengths, we get into ultraviolet, and then we get into X-rays, and then we get into cosmic rays. Much higher energy, much shorter wavelengths. All of them bring us information about the particular range of regime that they are characteristic of. So all the information we get comes to us from these chunks of energy, these photons that travel at the speed of light. And because we really understand well how these photons interact with matter that you and I are made of, and water and the air and so on, we can tell, looking at the light coming from this, what atoms are there, and whether those atoms are moving away from us or moving toward us, and how fast. We know from looking at the characteristics that the atoms over there are exactly the same as the atoms here in this room. So we know a wealth of information just from the light that comes from these things, and that's what we're really dependent upon to get all the information that's out there. Let me make another comment, which isn't too heavy into what will come later, but we also, let me refresh you about your high school, that everything is made up of atoms. And atoms are a charged nucleus with a negatively charged electron moving around it, or charged electrons moving around it. And in the nucleus, there are positively charged things called protons and neutral particles called neutrons. And each of those are made up of 3 different types of quarks. 3 types sit in a proton, and 3 types of quarks sit in a neutron. Different types give you the different characteristics. Those are fundamental particles. And then there's a few other particles that we really don't have to know too much about. And there's another whole set of particles that we've never seen, don't really know whether they are or not, but they might be, and that might be part of what's dark matter. So that's sort of what's coming, which is why you're not going to know much more after you have this. It's not a good sign for somebody giving a talk. But let's proceed. Let me give you a little bit of history also, where we are and what we know and why we know it. A large part of what we found out really goes back to this Hubble Space Telescope and really giving us a big step up in what we can see of the universe. We see an awful lot of stuff from the telescopes on Earth, but this gives us a tremendous advantage in looking out into the sky around us. And one of the marvelous things that happened in the middle 90s, somebody that took over that program decided, you know, what we ought to do is we ought to take some place perpendicular to the galaxy plane and look out where there's nothing and take a really long time exposure with this camera. And the exposure length was about 3.5 days. Really long exposure. And what they saw was, this is where they took it. This is the Big Dipper, and this is the area they pointed into where they saw nothing at all. Okay, so whenever they did that, this is what they got. Each one of these points is a whole galaxy. 1 billion or more stars in each one of them. And some of them go back so far in time that it's within about the first 10% of when the whole universe started. Well, we didn't know that initially, and the whole progress of coming forward to that is a big historical story in itself. But let me just briefly hit some of the highlights on it. Back in 1905, this woman, Henrietta Leavitt, discovered that variable stars change intensity, and the speed with which they change their intensity, whether it's a couple of days or hundreds of days, that varied in direct proportion to their brightness. So if you could measure the period of these things getting brighter and darker, you knew how bright it was. So once you know how bright it is, you measure the brightness, and then you can measure how far away it is. So if you know how bright and intense a street light is here, you can look out to Gresham, see the same kind of street light out there, and say, I measured its intensity, and I can measure how far it is from here to Gresham by measuring the brightness of that street light. That's basically the idea of getting started. And she measured 20 Cepheid variables back in 1912 in the small Magellanic Cloud and characterized that. And what it did, here's how they vary. They're not real smooth variation in these stars, but you can see this varies by about 3 orders of magnitude, and over about 400 days. And this varies by part of a magnitude, and it's only 7 days. So there is that big distinction. But what that means is, and remember in the old days, you had to take a photographic plate and expose it, and then go back a couple of days later, and a couple of days later. So you keep doing that, and you've got thousands of stars in a galaxy that you can see, and then you have to compare those. Tedious. The reason I'm not an astronomer, I started doing that kind of stuff, but enough already. Harlow Shapley was a fellow who used this technique that she had devised to measure the distance of Cepheid variables in our galaxy. And so he was able to come up with the dimensions of our galaxy using these Cepheid variables, and that was in 1918. So within a few years of getting this technique, they were able to start putting out the scale. And then this is basically what our galaxy looks like. If you were outside and looking in, this is what it would look like. And our galaxy is about 100,000 light years across, and our planetary system is about 60% of the way out to the edge, ballpark. So we're in an interesting place. Then comes along Edwin Hubble, who is the person that the Hubble Space Telescope was named after. And he grew up in Chicago and did quite well in school, but mostly he was known for his athletic abilities. He won all the competitions in his high school, except for one. I think he came in second or third. Ended up getting a Rhodes Scholarship, one of the first Rhodes Scholarship. He ended up becoming a lawyer. He majored in Spanish. Then he went in the Army. He never practiced as a lawyer, but he had his law degree. Then he was in the Army, World War I, rose quickly to become a major, got out of there, and for whatever reason he decided to go into astronomy and got his PhD in that, and then got associated with one of the big observatories, and started making some observations. And he was the first person that really started to find out what the real scale of the universe was using this Delta Cephei things, looking out at Andromeda Galaxy. And he was able to check some of the stars there and actually calculate that it was about 1 million light years away, much further than had ever been thought that they were going to be. And then using this technique, he started doing it to some other galaxies. And you know, stars are only so bright, so you can only carry that out so far. But he did it enough so that he was able to say the universe is expanding. It's not just stable, it's not just sitting there, it's not just our Milky Way, but it's really pretty distant. And not only that, it's expanding, it's getting bigger all the time. Well, you know, Einstein had come up with his theory of general relativity, and people had told him, nah, the universe is stable, and he had to adjust his equations to make it so that they would come out with a stable thing, because really, originally, he thought it either had to expand or contract. It couldn't just be stable, so he had to stick a constant in. He said it was the worst mistake he ever made in his life. I'll go back and revamp that later, but that's another whole story. But anyhow, this gentleman originally was really mostly known as an athlete, coach, all that, until he got into astronomy, and then he just excelled in that also. He coached. So whenever he found that the universe expands, we say now that it expands uniformly. And what that means is that if you have something spread out regularly like this, they start to move out, okay? Let me go back and show that again. Whoops. Okay. Now notice, whenever I can choose any one of these, and it's going to be the same for all of them. But notice also, if I go here and it's expanded, it's expanding uniformly. So if I'm twice as far away, it expands twice as much. 3 times, it expands, it's 3 times as far away. 4 times as far away in the same amount of time. So that means that this one is receding 4 times as fast as the one that's right next door. Okay? So the further away you go, the faster it appears to be expanding, to be moving away. Let me make a comment here. What does that mean? Does it mean the galaxies are whizzing through space, all the other ones, not us? No, what's really happening is, and I'm getting a little bit ahead of it, but we'll get through this part of it pretty quickly. I have a galaxy here, and it's turning so that the stars and so on are going through space, okay, and maybe it's twisting a little bit or moving a little bit through space. And the same thing with this galaxy over here. But we see that this one is really whizzing away from this one. What does that mean? What it means is space in between is growing. It's not that these are moving through space. These are staying pretty much the same in space, moving a little bit, but they're moving apart because space is growing in between them. It's being created. And also any photons, those electric chunks of matter, of energy that come from here over to there, as they go and as space expands, they get stretched out. So the wavelength gets shifted. Okay? So that's how we know that this one is moving away at a certain speed, and therefore how far away it is. Okay? To give you an estimate of what that means, the closest star that we have, about 4.1 light years away, it means that it's moving further away from us at about 2,800 kilometers per year. That's a distance from about here to Chicago or something like that. Every year it gets that much further away. With 4 light years, it's not really all that much, but it adds up over a few billion years. Well, if we're going so far out then to be able to really see far out, these Delta Cephei variable stars are only just so bright. They're kind of standard stars. We need something brighter than that to be able to go really far away. And what they found was that we can measure a supernova, which is a very characteristic kind of thing, and use it as a standard candle. So this part all of a sudden blew up, and it stays brighter than all of the brightness from a galaxy for about a week or two. So the name of the game in the past 20 years has been to try to find as many of these as you can, measure their brightness very accurately, and then use that as a standard candle to find out how far away it is. And they did that with dramatic success and found out in 1998, just 11 years ago, that the universe is not just expanding, it's accelerating in the rate of expansion. So now the combination of all this stuff and some other information that I don't have time to go into here comes up to give us a result that's like this. Standard atoms, like you and me are made out of, that's made in the center of stars and blown out and then condenses into planets and us, is 4% of the stuff in the universe. The dark matter, cold dark matter, talk about that a little bit later, is about 23%. Depending on who you talk to, it might be 25%, about 23%. And dark energy, and if we don't know much about dark matter, we really don't know much about dark energy. So I'm not even going to talk about that today except in passing a couple of comments. But really we're going to talk about this. So almost everything, 96% of it, is stuff that we don't know anything about. Now this dark energy is really very small, but it's pervasive everywhere. And let me make the other comment that I didn't mention in the introduction, that what I'm going to be talking about is mostly what's generally accepted as the science and explanation for these things. When you don't know what the answers are, and we don't know how quantum mechanics and general relativity fit together, they just don't work together, then you really don't have a final answer, and we know that. So there's a lot of conjectures thrown out. Well, what if this? Perhaps it's this. And so, but what I'm going to do is talk always about things that are pretty much accepted by people, and not give you some of the wild conjectures. There's a lot of those out there and interesting to listen to also. But we'll talk about cold dark matter. Make a comment that the dark energy is equivalent to having about 10 hydrogen atoms per cubic meter. Now that's not really very much. Now this is like E equals mc squared, Einstein's thing. You can talk about energy in terms of mass or mass in terms of energy. Well, to make it simple to understand, the amount of energy in a cubic meter is about the equivalent of the energy the 10 hydrogen atoms have in their mass. And that's throughout space. So whenever things are being expanded, that amount of energy is being created. Okay, so that's pretty much where we're at for that. How do we find out about dark matter? You can't see it. Well, of course you find out about it because of the things you can see, and you tell what the influence is on the things you can see and imply what's with dark matter. There's no doubt about where this is. It's not because you see the dark part, it's because you see the light part, and they're sprinkled out, and you kind of put them together, and it's all pretty much the same. And I can do the same thing on a wider area. Okay, so here we have the world laid out with the lights at night. And one other thing you might notice is that if you focus on this one part over here, notice that in South Korea, it's lit up with lights. In North Korea, not much there. So that has further implications. And you can do the same thing with a lot of other stuff here, but we won't go into that. So the original thing of trying to understand about dark matter goes back to Fritz Zwicky, who was kind of a irascible kind of guy, but he was a really good astronomer. And he started making measurements on clusters of galaxies. And he would, by using the measurements of the light that was coming in, know how these galaxies were moving with respect to each other, so they knew that they were in a cluster. And he said, you know, these things are moving too fast to be held together. And he couldn't go any further than that. That's what he said. Now think about that a little bit. It's like, you know, here you are on Earth, and you stick to the Earth, and if you don't walk too fast, you stay here. If you go really fast, though, you can go into orbit. You go even faster, you can go beyond orbit and go visit other stars, moon, or whatever. And if you go really fast, you can get out of our sun system. So the faster you go, the more it would take to hold something together, to pull you back. The gravity to pull you back has to be stronger the faster you go. And he said, these galaxies are moving around much too fast for the mass that I calculate is there from knowing about these galaxies and adding it all up. it doesn't work. And he just sort of let it go and went on beyond that. So then much later, this is the galaxy cluster that he was looking at, the comet cluster. And all these little fuzzy greenish things are each individual galaxies, not stars. Each has more than 1 billion stars in each one of them. And there's more than 1,000 galaxies associated with this cluster. Okay? So it's a lot of stuff out there. Well, then comes Vera Rubin, and she first did a lot of detailed measurements of galactic rotations, and particularly the Andromeda galaxy, the one I showed you, that rotation back in 1970. And she published, and this is the M31 Andromeda, now not just in black and white, but in full color. And the idea there is that, you know, if you have something that's rotating, if you have a solid material, then this part has to go from here to here in the same time that this goes from here to here. So this is clearly on the edge going much faster than the part in the middle. It's like a wheel on your car. The center part doesn't go around as fast as the outer part. They all have to get in the same angle at the same amount of time, so the outer has to go faster. That's not true with everything, of course. So if we take a look at our solar system, that's a wheel. We take a look at our solar system with gravity holding things, then the planet in the center has to go around much faster than the planets out here. The force is much less out here than it is in here, so it can go much faster. As a matter of fact, it has to go much faster to stay in orbit around the sun. And Mercury goes around 4 times a year compared to Earth. We go around once a year. And out here, it's a couple hundred years for Pluto. So we know that, and we can calculate all that. So that's very clearly defined. So here you have this galaxy now, and the things are moving around, and we're moving about 500,000 miles an hour around the center of our galaxy. You can calculate all those things and make the measurements at a distance, and what's observed is not something like this, but rather something like this. They're all pretty much the same. So there's something that's adding additional gravitational energy to make this work that way. And she measured several other galaxies, and she found that they're all pretty much the same. So something is happening in these galaxies that's adding additional mass that we can't see that's making them rotate in that kind of a manner. Well, you start looking at things. What could possibly be there that we can't see that's adding gravity? Well, could be neutrinos, and this is a while back. They didn't know too much about neutrinos, except they knew there was a lot of them. You know, through my thumbnail here, there's about 1 billion neutrinos go every second. But they have very little interaction, so it's very hard to find out about them. So it took them a long time to determine, do neutrinos have any mass or not? And finally they got some big detectors that were large enough and sensitive to a variety of different interactions, and they were able to find out that in fact neutrinos, that doesn't work. Okay, so scratch neutrinos. Mass of neutrinos is much, much too small, even with these large quantities, to make up for dark matter. So maybe we have dust clouds. We look out and we can see all kinds of dust clouds. I'll show you a couple in a minute. Maybe they're dark stars. You know, another name for big planets, or maybe a star that was starting to collapse wasn't really quite enough to start that thermonuclear reaction in the middle, so it stayed dark instead of burning. So we can't see those. So we got to look for all that kind of stuff also. Well, there's another, also, if you don't know a name for, if you don't know what something is, you can always at least give it a name. So they made a couple more names. One is machos. Massive compact halo object. Astronomers and physicists are nothing if not creative. And of course, if you got macho, you gotta have a wimp. So we have WIMPs. Weakly interactive massive particles. And so now we have to explore some of these different possibilities. Notice the dark stars could be one of the massive compact halo objects. It's pretty massive, big chunky stuff, okay? So that would be a possibility. First of all, dust clouds. And these are some really neat dust clouds, and we know that planets are being formed in some of these things around the stars that are there, and stars are being formed. And we can look at some of the things that, and we can see in these dark clouds these are clouds of dust that stop those photons from coming toward us. And we can very carefully make measurements and get a pretty good idea what this stuff is, what the total amount of mass is that's in those. And that doesn't really quite do it. We can even look, at all these galaxies, all these things. The reason they're lit up like that is not just because of stars, but it's spread out because there's a lot of dust there that's reflecting light to us. We can measure all that stuff too. And here's just another picture of another galaxy. Here's another one, and we can look in these in great detail. So if I go in there and I see all this dust around here, so we can really go into a lot of detail. And here's another one. Some of them are prettier than others, but you can see all the gas in there and you can make measurements of that. And so we make those measurements and dust clouds don't do it either. So scratch that. Okay, well, dark stars, well, how are we going to do that? Well, one of the ways to do it is, as a matter of fact, to look at a star. You can only see a pinpoint, but you look at a star and you see if the light varies because there's some big thing going in front of it. Now, it may be circulating around it or it may be just passing by. And you look at the light curve, so you get some of those, not enough of those either. Okay, so what do you say?
Is that an actual?
Yes, that's actual data. Yeah. Another way to look at things, this is quickly general relativity. Einstein said that if you have a large mass here, it's going to warp the space, and light follows space. So whenever you would think that the star is out here and the light curves around, it really looks in a couple different directions. It looks like it's down here, and also because gravity has caused this to warp around, it looks like it's up here. So you see two star images of the same star. And by knowing the displacement, you can also measure the mass of that and get a lot of useful information. So one of the things that you can do is be an observer down here, and this is the observed image from this observer, and here's the star, and here's some massive halo object moving across, and it's going to cause the space to warp and bend the light so it gets a little bit brighter as this goes across in front, and then it goes back down again. So you get a light curve that looks like this. So they make a lot of measurements of that. And as a matter of fact, in the 90s, they must use a lot of graduate students. They had something like, well, let me show you the next one here. Here's a typical kind of star field you might use. Here are data points. And they had something like 12 million data points to go through. And they found 7 objects that might have something like this. So not likely that you're going to have that observed either. Here's something where you see the brightness that's observed, and then you go and you take a look with Hubble, and you see, sure enough, there's where it is. So they confirmed a lot of these different kinds of things. But now we know dark stars are probably not it. And also, now we've looked for all these massive things that would go and would obscure the light from stars in a variety of ways. And we find that that's probably not it. But, maybe we just didn't look enough or carefully enough, or our data's not quite good enough to be sure. But for the most part, machos are out of it. Yes?
Well, I'm just trying to understand something, because you're looking at stuff that would be kind of static masses, right? But yet you were talking about
Nothing is
energy
static.
is growing. Right. Because you said the energy was growing, so why would you look for an energy source that was growing?
We're looking
Things
at
that seem
dark
like
matter
static
now, not
masses.
dark energy.
Okay.
We can talk more about that, but all the things, nothing is static in the universe. Everything is moving with respect to everything else, or it would fall together.
I guess I'm just thinking about these massive things you're looking at.
These are massive things you're looking at that are going across in front of light-emitting things, so otherwise you wouldn't be able to see them. Okay. So that really kind of gets rid of a large number of the possibilities for this dark stuff being things that we're usually aware of in our normal type of mass. So now we have to start talking about weakly interacting massive particles. Now we're talking about fundamental particles like protons, neutrons, except they're different and they don't interact with them very much at all. But they do interact gravitationally. Well, do we have much evidence for anything like that? Remember, we're talking about a possibility of Einstein warping, says mass can warp space, so that if we have a quasar or a galaxy or something out here, we look out, and if we look, we would see A imaged here, like with that star before, and B imaged here, like we saw before. So we would be able to see those things from two different directions, and we kind of weigh the galaxy in here by knowing its mass variation. And also, if there were another galaxy or another quasar in here, we would get two other additional dots. But now this is not as far away as this, so they're going to be different redshifts. So we can measure the redshift of these different dots, and knowing that this dot is not with this one because the redshift is not correct. So we can associate these two dots, and we can associate these two dots, and you do that with a whole bunch of stuff up in the sky. Really gets complicated and messy, but that's what people do. So you can start plotting out things. And let me just show you a couple of pictures of things that show up that you don't normally see. But these are false color images where you can see this is clearly where the big mass is. And this forms images around it. Now this is a little bit different, maybe it's slightly different direction, but it's not unusual to find things like that. Here you see some of these curved things, okay, little curves. So there's gravitational lensing that you can find throughout the sky. And if you look for even more, these are obvious kinds of things visually, but if you look more subtly, you can find an awful lot more. And that's the kind of things that people do. One of the things that's a really good example of dark matter that's kind of understandable for you and I was found in the bullet cluster. It's a great dark matter example. And you may not be able to tell it, but here's a cluster and here's a cluster. And as a matter of fact, this is sort of how they've been identified. And by knowing the way those photons come to our eye and measuring the recessional velocity and the approach velocities and so on, we're able to say that these galaxies are two and separate clusters of galaxies. And not only that, they know this one's going this way and that one's going that way. And at the speed and so on, they know that they had to go through each other not too long ago, a few billion years or so. So basically they went like that. Okay, so that's what's happened. Now within this cluster, there's a lot of gas that's just kind of floating around. Not very much compared to what's in the galaxy itself, but there's stuff in between. It's not as empty as free space in the universe is. So whenever these go through each other, the gas from one is going to be moving in this direction, the gas from the other, so it's going to collide, and it's going to interact. And it's going to make enough X-rays that we might be able to see it. So you look for X-rays, and that's what you see. And as a matter of fact, this shows where the galaxies are. This is the gas associated with that, and it got held back by the flowing through the gas here. They're going like this, and they interact. Well, there's an awful lot of stars in the background, so maybe we can use gravitational lensing to get an idea, is there any extra matter in there that we can't see, that doesn't give these X-rays, that would be dark matter that we're looking for. And as a matter of fact, you can. And there it is. Shown in this is a false blue thing, because otherwise it's dark matter, you can't see it, right? But they imply this by that, and as a matter of fact, it traveled right with it, because dark matter doesn't interact very much. It just goes right through each other. So there you are. Yes?
Just to make sure.
Oh, okay. Shall we do the questions at the end?
Well, I just want to know, was there a blue shift, or is that imagined?
Oh, this is just false color.
Okay. Not there.
Not there. Because you can't see dark matter. Yeah, let's hold the questions to the end. That'll be the easiest, then we can. But I think we'll have plenty of time. I don't have a lot longer to go. So if we take a look at these all together, here are the clusters, and here are the X-rays from actual matter, and here are the implied positions of the dark matter. So that's one good example that we have. And I'm not sure whether I have other things stuck in here. Okay. This is standard matter, and this is dark matter. And this is another one where, by using lensing, they were able to imply where the dark matter exists. And this is where two clusters went through each other, where these we saw them going side to side. Here they're kind of toward us and from us, so they went through that way. So it's all kind of circular this way. So this is the dark matter that you see in those clusters that is intensified. Okay, so we know that it's pretty valid. We get a pretty good idea of what it is in terms of quantity, and it only interacts gravitationally. Well, since we have a wealth of data and a lot of capability with our instruments, one thing we can do is we can say, well, let's use, for instance, the Hubble Space Telescope, and we look out and we find out what kind of dark matter might we get with a certain redshift, here at 3.5 billion years, and then at 5 billion years, and then at 6.5 billion years. And it gets much more complicated than what I've just explained to you. But with a big computer program, you're able to punch through an awful lot of stuff. And we can go into that a little bit more if you want, but it gets pretty hairy. And this is what dark matter looks like looking out in one particular direction. It's about 1.5 degrees by 1 degree. Okay? It probably will be a little more chunky this way, but the resolution that you have for the redshift is not as good. But that's the implication. Dark matter is everywhere. It's a little clumpy, but it's everywhere. Here's a little bit better presentation of it. Think about the early universe that we didn't really talk about, but you have the expansion, the Big Bang, and things get thinner and thinner, and they're blowing apart, and it's all just particles and gas at that point. And now, after a while, gravity has to start taking over and pulling some of these things together. Now, the mass that you and I are made of, and all the Earth, that has gravity and starts pulling together. But also, same thing is happening with dark matter. Dark matter has gravity, so it also starts pulling together very much the same way that the normal matter that we're made of pulls together. So, as it clumps together, you get galaxies and you get stars and then galaxies and clusters and so on. And this is what you end up with, very much like what we see when we look out in the sky today. And if you do a computer model from this distribution of gas and dark matter, then after a period of time, it starts clumping up, and then it starts clumping up some more, and it starts clumping up some more. Now, this is a computer model, so you can control how much mass you have of whatever type that's in there, and this is what looks very much like what we see whenever we look out and plot large areas of the sky. This is very much what we see. So that's pretty accurate. But that's accurate only if you make certain assumptions about the dark matter that's there. If you say dark matter is there, but it's warm, meaning that it's moving like half the speed of light or something, as it's really moving fast, so gravity is not able to clump it nearly as well because it's going too fast. It just keeps zooming. Then this is the smoothed out kind of thing that you see from the model, and that's not what we see in reality. But if you have cold dark matter, meaning it's only going a couple of % of the speed of light or less, then it clumps up like this. And that's exactly what we see. And if you don't have dark matter, it doesn't clump up this way. It doesn't clump up enough. So you have to have dark matter, has to be cold dark matter, and that's what reflects the stuff that we really see. There's a lot of stuff going on now. These are studies where they're going to put them down into deep mines to get rid of all the other interactions and cosmic ray interactions, radioactive material, and so on interactions, to isolate it as much as possible. Here's another one that's going to go down. Here's one that's down in the deep ocean, strung out. Here's another one going to go down in the mine. Here's one that looks up in the sky for particular kinds of radiation that come whenever particles hit the atmosphere. Here's one that's going up in a satellite. There's about 20 different experiments of this sort that are going on that haven't gotten any data yet. The Italians say that they got some positive data about 2 or 3 years ago that nobody believes in because nobody can repeat it. They can't explain it away, but they can't repeat it. So maybe there's something going on we don't know. Either the experiment's got a problem or it's got something that we don't understand, or who knows. So there's a lot of stuff going on that way. And then going up from the other direction, instead of just looking at nature, we'll try to create some of these things. One of the big possibilities is that the stuff that is normally understood in our particle physics thing that we put together back in 1985, we kind of understand a lot about quarks and protons and neutrons and electrons and so on. Well, that gives us a whole family of particles, most of which we never are kind of exotic, we never see. But there's a possibility that there's another whole range of particles above that in energy, but we don't see those in our everyday life because it's too much energy. Well, this is the Fermi Lab out near Chicago, just west of Chicago, and they keep cranking up the amount of energy that they can collide particles with. The idea is that if you smack particles together, you have enough energy that you can create all kinds of stuff. And if you make some of these other higher energy particles, you have enough energy to make them in mass, then you can look at those with experiments. And the more of those you can make, the better chance you have of, you make a gazillion of them and you see 2 or 3. That's what exactly happened with neutrinos. Well, they're trying, but they're just on the edge of being able to do something like that. But CERN, which didn't manage to get online last fall and had some problems trying to get on this spring, hopes to be online in the fall, and that's about 8.5 kilometers in diameter, so it's about 25 kilometers around, 300 feet underground, isolate it and keep it salt stable and not interfere with all the other things going on. And they will be able to generate masses, energies, masses that have an energy that's up to 15,000 times the mass of a proton. And if they're able to do that, then they should be in the range where we would expect that if their dark matter is from particles, the biggest candidate is the neutralino, and it's about 200 to 1,000 times the mass of a proton, so they should certainly be in that range. And there's other things also. So there's a whole bunch of things just about to happen in the next 4, 5, 6 years. Exciting time to be aware of this stuff and to see what's going on. And that's pretty much it. Except that, quarks, neutrinos, mesons, all those damn particles you can't see, that's what drove me to drink. Now I can see them. So that's
just a quick question, where you finished with colliders. As I recall, about 20 years ago, we had an enormous super collider being constructed in Texas, and budgets killed it. And my question to you is, what would it have been able to do had we continued over what existing colliders are doing?
I don't remember exactly, but I think it would be in the same regime as the CERN, the one in Europe. And the big kick to CERN was the fact that the Texas one died. I don't know, politics and all kinds of things got involved with that and funding. And then CERN, because that got killed, CERN picked up the mantle and started carrying it forward. And of course they got a lot of funding from us, but also from a lot of other European countries. There's already a lot of activity there in CERN. This just is adding on to that. So it's a tremendous advantage. There's a lot of real talent. And of course, CERN is the area where the internet was devised. They are the people that put it together so they can communicate with people, scientists all over the world, and exchange information and stuff. And from that is where Al Gore didn't really do it, those guys.
Have they finished the CERN one? Is it functioning yet?
It's finished. And then when they turned it on I think it was last fall, they had a problem with one of the magnets. So they had to warm everything back. I guess it was in the spring. They had to warm everything back up, and they hope they'd be getting down in the fall, be able to get it back up and running in the fall. And then they have to stop in the fall because it uses so much power that they can't use the power from Europe during the winter when they need it for other things. So they have a break of about 3 or 4 months in there. So they had to shut down. And they decided they couldn't bring it up and do anything in the fall because there were too many problems. So they put it back down and said, we'll do it next spring and we'll work on all these problems. So it should be up and running again, but they won't actually be, very soon, but they won't actually be doing experiments until the fall because it takes them that long to get things lined up and everything squared away.
Great. You were talking about supernova in your nice slide up there. But you didn't mention what else supernova told us about the universe, and that was the age of the universe. You actually had it on top of your slide. But it told us about the age of the universe, 13.7 billion years old.
Yeah, there were a combination of things that allow us to know what the age of the universe is. One is the fact that you look out and you see how fast things are streaming away, and it gives you a scale of the universe. And in the equations, there's a thing that tells how fast that is, and that's one number. But the one that really tied down the 13.7, it used to be, 12 plus or minus 3 kind of thing, is the background radiation from the Big Bang. The 380,000 years after the Big Bang, the electrons clumped onto the protons, and all of a sudden, the photons did not interact strongly with these charged particles. So that gives rise to this background radiation, and we've been making a lot of detailed measurements about that. And the size of the variations in the temperature and the scope of it really locks that down pretty tightly. Yeah. Well, I'm sorry. Jesus.
I have a loud voice.
It doesn't.
They might not hear.
You mentioned Pluto as a planet, and there's some debate.
Us in the old school still consider Pluto, but the thing is, that's a never-ending thing. What she's speaking about is that a little while ago, there was a museum, an astronomical, whatever you want to call it, in New York City that put up this planets around the sun, and they didn't include Pluto. And they said, Pluto's not a planet, it's a dwarf planet, if you really want to say that, meaning it's very small. Well, a lot of us that grew up with Pluto as a planet still think of Pluto as a planet. But on the other hand, then, now that we see more things, well, where do you stop? Because there's stuff just a little bit less than Pluto, and then a little bit less than that. It's sort of like, how big is a moon got to be a moon? Because when you start sending these satellites out to look at other planets, they don't just have a couple of moons. They've got like a gazillion of them. If you include a rock that's only 700 feet across, or 700 miles across, is that a moon? Well, so the definition now of a planet is something that dominates its space.
Two things. I can't remember the number, but I'm hoping maybe you can, because it was impressive to me what things would have been like about 2 billion years ago in terms of how bright the night sky would have looked if we looked up to it, given that things are moving at a faster and faster rate. So if you can remember, it might give us all an impression of just how things have massively changed in terms of what the appearance of the universe would have looked like, what the appearance of the night sky would have looked like in, halfway through the history of the Earth, which I think is about 4 billion years, but I can be corrected. The second thing I want to ask about is
how bright the night sky would be.
Would have been 2 billion years ago, given that it increases and further away. So my understanding is it's been incredibly bright compared to what we see now. But the other thing is, why, you drew pictures of blue stuff. Well, you can't see it. You don't have any data for it. Why isn't the theory of gravity just wrong? Why isn't this just another made-up constant to account for what doesn't work?
Okay, first question, I don't know how much brighter it would have been. It probably would have been brighter, but how much, I don't know. If you went back, 8 or 10 billion years, then it would be significantly brighter, but I don't know what the numbers are. In terms of, is gravity wrong? Well, we know Einstein's general theory of relativity is wrong, and we know that quantum mechanics is wrong because they don't really agree at the small levels. And as a matter of fact, whenever you go and you calculate what the background energy should be in the universe in nothing, quantum mechanics comes out and gives you a number. Relativity comes out and gives you a number. And those two numbers are different by a factor of 10 to the 120th. That is 1 followed by 120 zeros. Okay? Now, there have been some other suggestions where, for instance, if you look at the rotations plots of galaxies and how it changes as it goes out, it turns out that some guy came up with the interesting observation that, if you go out a certain distance in each one of these galaxies, gravity works really well. And if you go beyond that, if you say that it diminishes at a certain rate, it fits all the data. So maybe gravity doesn't always go 1 over r squared forever. So people went back and started looking at other things, and I remember there were some measurements made, big high towers, but it turns out that if you go to even further things, it doesn't work then either. So what I think you're getting to is the fact that there's always some other half a dozen theories, people coming up with great ideas to try that don't work out. I mean, that's why I think Einstein is really a genius of a science, because most things, like the first time equals mc squared and all that, things were coming in physics to a head, and if he wouldn't have come up with that, somebody else would have. But the general relativity of work space, that would have been another 30 or 40 years, I'll bet, and most people generally think that. I mean, that was a really off-the-wall thing. So what we're looking for now is something really off the wall that's going to pull all these things together. String theory tried to pull it off, and they gave us some insights, but it still hasn't been able to do it. I'm sorry, you've got to have a microphone.
Al, you're next.
Okay.
Now, you showed us the galaxies that were colliding and that there was dark matter in those galaxies, and it kind of looks like the dark matter is following the galaxies around. But when I go back to your one of your early slides that says there's a lot more dark matter than real matter, it's kind of the galaxies are following the dark matter around, and that the dark matter is really controlling our universe. Is that what's going on?
Yeah, actually. The thing is, there's a lot of dark matter there. And the reason that things clump in the way that they do, according to the models, is because of the dark matter. That pulls other dark matter together, and it's sort of like a swarm, okay? Like whenever regular matter starts falling in gravitationally, it starts smacking each other, okay? It transfers that gravitational energy into heat energy, which is what heats up the stars and gets that thermal stuff going. But dark matter, it doesn't interact. So it goes right past. And it doesn't interact. It goes out here, whoa, back here, whoa, back here. It does that kind of thing. But it always keeps going past each other. But the gravitational center is still helping to pull in all the normal matter, so that's exactly right. And that's why those clusters of galaxies are held together much more than they would have been otherwise. Yeah.
Are you in that string theory?
I'm sorry?
String theory.
Let me just make a couple of comments about string theory, because that's sort of a really hot topic all the time. The idea with string theory is that, well, in standard theory, we only know about points, okay, particles, they're really, really small, and then they go down to a point. Well, points in mathematics are really uncomfortable. 1 over 0 is big, no matter how you say it. So you have to learn to renormalize and do things, and they work out all that kind of stuff. But string theory gets rid of that in all one fell swoop, because it says, well, you never really get down to 0. You get down to 10 to the minus 33, which is pretty small, but it's not 0. And so all the particles, it says, are really just small pieces of string type, they're small line, a filament. And the fact that they vibrate like a harmonic on a violin or any other string instrument, they vibrate, and different vibrations give you different particles. And then also it says that, well, there aren't really just 3 dimensions, there's really more like 11 dimensions if you include time. So not only did they vibrate in our dimension, they vibrate in other dimensions also. So it gives you an awful lot of different possibilities and combinations and stuff. But one of the wonderful things that really got a lot of good press for string theory was the fact that gravity naturally falls out of it. Because gravity is a string that's not just a loose end string, but it's a loop. So it can move swiftly in various places and in different dimensions without being held up, which may be one of the reasons why gravity is so weak. It's able to leak out into other dimensions, and we only feel part of the effect of gravity. So there's a lot of neat things going for string theory. The only trouble is when you do calculations with it, first of all, you don't know which string theory to use, because string theory you thought 10 to the 120th was big. String theory, it looks like, has the possibility of 10 to the 500th possibilities of ways to combine these different dimensions to give us, I think, well, how do you choose which one it is? We don't know. There's some other, well, okay, that's fine.
You had a slide that showed an entire galaxy, and it appeared to be circling. My question is, do you know how fast that circling is, and do all planets, all solar systems rotate at that same speed?
I guess the question is, galaxies rotate, do they all rotate at the same speed, and how fast? Well, yes, all galaxies, all is a strong word, but galaxies rotate or mush around in various ways. There are circular ones as well as these flat disk things. There are barred galaxies, all that kind of stuff. Not all at the same speed. Our galaxy, and then, so it depends on where you are in the galaxy as to what the speed is. At this location where we are now, we are moving about 543,000 miles an hour in some direction. But that shouldn't disturb you because we're right now moving on the surface of the Earth about 750, 800 miles an hour to the west, to the east. The sun comes up in the east. Okay. That's what a physicist, you don't memorize things, you work them out.